Thank you. Good. So, in the session before the coffee break, we talked about several different strategies. With our biggest underlying question is basically, what is the organization of the human brain network, and how can we study this in terms of the healthy and diseased brain function? And in particular, this session, we will talk about centrally connected hub regions and how they might display an important feature of the human brain network organization. And I really took this as an educational talk, so I will just have a couple of basic questions that I want to address and issues that I want to discuss. And I'm going to begin with some of the very basics of the hub type of theory. Asking the question, what are hubs? How can we select them? Once we have selected them, how can we categorize them or give them a label? And what is the level of connectivity or the relationship between hubs, and how might they form core structures in networks and brain network in particular? And later on in my talk, if there's time, hopefully, I will discuss a little bit more advanced issues. And these are really open questions in the field, namely, how can we compare networks, and in particular, how can we compare hub structures across networks, in particular, for example, when we do case control studies. And a final point is, what are the general things that we have to consider when we're analyzing hubs? And again, in particular, in context of patient control studies. And like I said, these are really, really open questions. So what are hubs? Well, I think this is the easiest question, because we all have a very good intuition of what hubs are and what they're doing, because we encounter them basically all the time, right? We see them in flight networks. For that matter, Singapore is of course an airport hub. If you want to go to the other side of the world, to Australia, and you come from Europe, most of the time you make a pass over in Singapore. But we also encounter hubs in terms of social networks, right? We all have those friends that are participating in all of the different parties. And more finally, we also encounter them in many computer networks, right? I think all of us have, in that sense, a computer hub at home, which routes all of our internet traffic. So we encounter hubs very regularly, and we all have a very good intuition of what they're doing. But how can we formalize this, right? How can we basically build this into a mathematical module to establish what hubs are, and how can we study them? So one of the first definitions of hubs, and one of the I think the biggest discoveries in network science in general, was done by Barabasi in his 1999 science paper. One of them, I think, most of the most cited papers in science in general. And what he noticed is that if you pick a random network, right, and this will be a network, a random network is a network in which every one of the nodes have an equal level of degree. So the level of connectivity of a certain node in the network is randomly placed. Then the degree distribution, meaning that if you make a histogram of the degree of every one of the nodes, then the histogram would be would have a bell-shaped curve form. However, what Barabasi noticed is that if you take many networks in nature, like flight networks, communication networks, social networks, right, the one we previously discussed, then the degree distribution does not follow this type of bell-shaped curve, but rather, in many cases, it has a power law function, right? If you take a log-log scale of the degree distribution, then it follows a straight-off linear curve. And this gives the indication that apparently the level of connectivity or the level of degree in the network is not evenly distributed, right? Apparently there are some nodes in the network that have many, many more connections than others, but there are only a very few of those, right? So the majority of the network has a very low degree, but there are some nodes that have many more connections than others. And this was actually the start of an entire field of science of showing this type of scale-free or right-tilt degree distribution behavior of many different types of networks. And for that matter, there are actually multiple types of forms of organization of networks that can display such a type of power law or right-tilt distribution of degree. So there's not just one form of topology that can display this type of behavior. And in network neuroscience, most of the time we take a little bit of a more lenient approach. So we're not only looking at this power law distribution form, but like I said, most of the time we're satisfied with a right tilt or a heavy tilt degree distribution, right? So if in this case, if you make a histogram out of all of the degrees of the nodes of the network, then if we see a right tail or a heavy tail, that means that apparently there are some nodes in the network that tend to have a higher degree than the far majority of the nodes of the network. And these are in particular the nodes that we now intuitively tend to call the hub regions. So how can we select hubs, right? What are the characteristics of hubs? Now, here too, like I said, it's really an intuition because there is no straight definition of what a hub is. And if you just look at network neuroscience literature, there are many flavors of how people tend to select hubs. So it is really, in essence, it's up to you to decide what you think a hub is. But I will display a few general options that people have considered. So I will just quickly go over the options, but there are many more on how you can select hubs. But it boils down to the overall suggestion that hubs should be central nodes within the overall network structure. So the first metric that we can look at is degree, which would be in that sense, the most simple one. And degree would simply be counting the number of edges per node and then just taking the nodes that have the most edges. And this could be, for example, the top 10 most connected nodes of the network, and we can call those the hubs of the network. In more formal terms, that would be the degree centrality. We can also take a little bit more complex metrics, a metric that we call closeness centrality, and basically closeness centrality looks at what is the average distance from a node to any other node in the network. So if we have the green node, then how long does it take to travel from that node to all of the other nodes in the network? Well, this will be the path length, if you will, right? And we do that for every one of the nodes. Then we list all of the nodes according to their path length or their closeness, to how close they are to the other nodes in the network. And then again, we take the top 10 as the most closeness or the highest centrally connected nodes in the network. We can also take that a little bit more advanced still by not just looking at the distance from one node to all of the other nodes, but what if we would basically look at the level of communication, in this case computed by the shortest path length from any node to any other node in the network, and then we simply count the number of times a certain node is passed. And in this case, for example, if we take this path shown on the slide, the green node is hit once, so therefore it has a +1. We do that for every one of the possible combinations of blue nodes, and then we get the metric of between centrality. So this really captured the intuition that a node should actually be a facilitator for short communication paths in the network. Right? So the nodes, in this case, the top 10 of nodes with the highest between centrality could then be our hubs. There are also other metrics that capture centrality proposed, which are a little bit more advanced and also a little bit more mathematically complex. So two of them, which are, I think, regularly used, are eigenvector centrality and PageRank centrality. So basically what they're doing is they're saying, well, if a node is central in the network, if its neighbors are also central. So and the simplest example is a social network here. If you are a big player in a social network if you are connected to a lot of other big players. Now, one way to mathematically formalize this is in the following way. So if we have a graph, then the graph actually, we can represent that in terms of an adjacency matrix. Right? We've talked about that in the previous lecture. So the adjacency matrix simply captures the amount of connectivity between every one of the nodes. Now, given that it is a matrix, we can do an eigenvector decomposition of that. And basically, if we do that, we get a collection of eigenvalues and eigenvectors describing the complexity of the network. Now, it has been noticed that one of the eigenvectors, in particular the one actually with the highest eigenvalue, is actually a metric of centrality, the importance of a node. One that exactly captured the description that you are important if your neighbors are important. And that is the metric of eigenvector centrality. It's a very simple metric to compute, but like I said, the underlying mathematics are a little bit complex. Now, another metric that is actually a little bit related to eigenvector centrality is PageRank centrality, and that is based on the random walk property of the network. So Bratislav already nicely mentioned this. So basically the eigenwalk centrality is you place a walker in some of a seed in one of the nodes in the network, and then you let it randomly diffuse across the network. So for example, if we start in the red node here, it is a 50-50% of taking one of the edges. So for example, apparently it took this one, then it's another 50-50 chance, etc., etc. And then basically the walker walks around the network following the topology of the network. So if we do that in a simulation, it can look a little bit like this, and then we can do that over multiple starting seed nodes, etc., etc. And in the end, we can simply count how many times a certain node is passed in the network, right? So this would, again, give us a very nice intuitive way of what a hub would be, right? Because if you would start a random diffusion process in the network, and then how many times a certain node is hit, would give us a good indication of the level of centrality of a certain node in the overall network. So this is a question to you guys. If you would look at the final end result of the simulation, right, which distribution actually does this represent? Well, mathematically, it's actually exactly the degree, or almost the degree distribution. So if we would have a random walker and we let it walk around a binary undirected network, then we're just going to almost end up with the degree distribution. So these metrics of random walkers and PageRank centrality actually make more sense or have more influence when we do it on directed networks. And in particular, when we allow also another level, which is what they call teleportations in networks. So, and the teleportations is basically that a random walker can actually randomly switch to a certain node on which it's not connected with a very low probability. And the reason for this is that you don't want to have a random walker get stuck in a certain endpoint in the network. Now, this is actually a very famous type of centrality metric, the PageRank centrality, which is the random walk with teleportations, because it's the founding algorithm for Google. Well, I don't think that needs any introduction, but apparently it can clearly and very elegantly select the centrally connected nodes in the network. And it has also been, with success, applied in network neuroscience. There's a paper by Boombarger and colleagues in Cell in which they, for example, use this approach to select centrally connected hub nodes in the C. elegans worm. So this shows that even these more difficult concepts of centrality can be very fruitfully used in selecting complex network structure and selecting centrally connected nodes in neural systems. So to summarize, where we can select hubs in different ways, right? And we have looked at degree, and we have looked at closeness centrality, betweenness centrality, and like eigenvector and PageRank centrality. And you can basically pick any one of them. The one basically, it's up to you to select which one of the hub definitions you find to be the most logical. But you can also actually say, well, perhaps it's a combination. Right? I'm not satisfied by a certain node to have one of these properties, but who knows, right? I actually want to have, I find nodes to be central if they have a high degree, but also if they have a high pass count and or have a high eigencentrality. Or for that matter, actually, you can also make up your own centrality metric, right? If you have a good argumentation of a certain, if you have a good argumentation for why a certain node should be central, then I think this is purely justified to use that. Or for that matter, you can also perhaps also say, well, a node should not have a certain property. And all of these strategies have been extensively applied, I think, now to the human brain as well as for the animal brain. And studies have very consistently, I think, now selected centrally collected hub nodes in the human brain. And for that matter, not just for the human brain, but I think in nervous systems in general, right? There's been, I think, a growing consensus that any type of nervous system tend to display centrally connected hub regions, arguing that perhaps having hubs and having types of the other central structures is a key feature, a fundamental principle of wiring of the human connectome. So once we have established these hubs, right, what can we more do with it? Now, one of the things that has been extremely fruitful in network neuroscience is to categorize those hubs and then look at the behavior of different types of hubs and their role in brain function. And what I mean by categorization of hubs is that if we look at this toy network here, and if we would be able to select the different functional systems of that network, right? So let's assume that these would be a definition of the different functional modules that could exist in the network, right? In this case, we have 3 different functional systems. Then if we look at these 2 centrally connected hub nodes here, both in orange, but the dark orange and the light orange, they're both hubs if we select them on the level of degree. So they're both highly connected nodes, but they clearly have a different hub function in the network, right? We could, in particular, if we look at the level of connectivity of a node within its own central module versus its level of connectivity and its role in connecting different modules, the 2 nodes actually display a different type of behavior. We could argue that the dark orange node is only, in this case, so it's exclusively connected to only nodes of its own flavor, while the light orange node is actually half of its connections are connected to nodes of its own kind, but the other 2 connections that it has is distributed across the other networks. So the light orange node in that sense is perhaps a node that is more connecting to other modules. It plays a more integrative role in the overall system, while the darker orange node is much more of a node that is crucially important for its facilitating communication and integration across its own module. And we tend to distinguish between those 2 as connector and provincial hubs. So how can we select them in a more formal way? Well, there has been 2 basically properties of these nodes proposed in literature by Guimera and colleagues that might capture this type of behavior. Now, the first one is the participation coefficient, which basically captures the distribution of the connections of a certain node to all of the different modules of the network. And the other metric that is proposed is the within module degree z-score, which is given a node, how well is it connected within its own module. Right? And in particular, it basically contrasts all of the nodes that a certain node is participating in that particular module, and it then looks how many more times this node is connected within its own module as compared to its neighboring nodes. Now, Guimera and colleagues then said, well, if we have those 2 different properties, right, these 2 different metrics, we can actually define a certain space, and we can then place every one of the nodes within that space, which reflects whether these are more connector nodes or more provincial nodes. So again, if we go back to our toy network here, then we have all of the module definitions, right? So we have the 3 modules, and then we have the 2 centrally connected hub nodes, again, the orange nodes. So then if we would pick this dark orange node, then where would it fit into the space of the spanned by the participation coefficient and the within module degree z-score? Sorry. If we chop up this space into a couple of blocks, in this case 7 different blocks, right, R1 to R7, where would the dark orange node fit? Would A be in R2, B in R5, or C in R3? Who dares? A very enthusiastic crowd here. All right, no one dares, right? Okay, we could do a vote. Let's do a vote, right? I'm going to waste my time on making a vote, right? You guys should participate. So who thinks the node will be in R2, right? So R2, I will help you a little bit, will be a low participation coefficient and a low within module degree score. Who votes for R2? All right, it's going to be long this morning. Who votes for B? All right, a few votes. All right, excellent. Who votes for C? All right, there are some people that vote for D. Well, there's no D. So let's do one more. Who votes for A? Who votes for B? Who votes for C? Excellent. Well, I think the right answer is indeed B, right? Because the participation coefficient is relatively low, but the level of within module degree score, it has a high degree compared to the other nodes that this node is, in the module that the node is participating in. All right, let's do one more to pick the other node, right? The light orange node. Who votes for A here? Who votes for B? Who votes for C? All right, people are a little bit more hesitant. So here too, the within degree z-score is relatively high, right? It has a degree of 4, while all of the other nodes in the module has actually a degree of 2. but the participation coefficient is also relatively high. So, and this is what we would call a connector hub. So basically what we could say is that all of the connector hubs would fit in R6, while all of the provincial hubs would fit in R2. So we can do this, of course, for every one of the nodes in the network, and then we can capture the different type of behavior of the individual nodes, in particular the centrally connected hub nodes. So what are the other regimes of this space, right? And these are a little bit more mystical. They're a little bit more difficult to understand. But what type of node would fit in R3 or R4? So these will be nodes with a super high participation coefficient, but are super low, actually, within degree z-score. Well, they're not. So, for example, a node, if the network would have looked something like this, a node like this would fit in that space. Or even worse, if we would have a node that is labeled to a certain community, but actually not connected to that community. And these would be, for example, someone that has that is registered to a fitness club but never goes there. Actually, right? You're registered to a fitness club, but you only go to tennis or your chess club. Well, I think we've all been there, right, with one of those annual subscriptions. So once we have selected those hubs and we have categorized them, then we can actually go one level up and say, what is the level of connectivity? How are these hubs basically related in the overall network, and how might they facilitate a certain type of behavior in the overall system? So one way to capture the level of connectivity between hubs, or the relationship between hubs, is the so-called K-core structure. Well, the K-core structure, or in this case, in the example giving a 3-core structure, would be to select the existence of a subnetwork of nodes that together share a level of degree K, in this case, level of degree 3 or more, in the network. So if we would take our Tor network here, the 3-core would be this subset, right? If you take the subset of nodes, the red nodes, and you, if I did it correctly, all of the nodes should share among themselves a degree 3 or more. And this too has been, I think, interestingly applied to the nervous system of the brain, in particular the human brain, in which people have captured a centrally connected core structure, in particularly focused around the more parietal regions of the brain. A related, but mathematically not the same, and I think also conceptually not the same, is the rich club structure. Well, the rich club structure is a little bit more lenient than it is in the K-core, basically saying, what is the level of connectivity between the centrally connected hub nodes in the network? Well, in other words, are the centrally connected hub nodes in the network perhaps more densely connected than you would expect in a certain average distribution or an average degree of the network? And that's illustrated by the following, right? So if we would have our Tor network in the top, then the centrally connected nodes, the red nodes, could be connected in 3 different ways. They could be very low connected, meaning there are only a few connections between the centrally connected hub regions, meaning that the hubs would be really working almost all independently from each other. They could be averagely connected or medium connected, meaning that they would have a certain level of shared connectivity, which would be on average compared to the entire structure of the network, or they could be very strong or very densely connected. And this is very elegantly captured by a formalization of this concept by Colisa and colleagues, in which they simply said, let's, for all of the length of degree in the network, for all nodes, for all different levels of degree, we simply count the number of edges present between that subset of nodes that have this level of degree, and divide it by the total possible connections that this subset of nodes could display. And one can do that for every one of the levels of degree. So you get this type of figure structure in which on the x-axis you have all of the levels of different of degree, and then on the y-axis you have the level of connectivity shared between those subset of nodes. So if you do that for the human brain, you get something like the dark black line, right? So the level of connectivity apparently increases when the level of degree of the nodes increases. Well, actually, this is almost a trivial behavior, right? If we have a certain type of network structure, and then we start selecting those nodes as hubs that have more and more and more degree, then, of course, they also have a higher probability of sharing a certain level of connections because they are high degree. So almost always, we compare this to the random null model, as we nicely saw before the break. We saw the importance of selecting a null model. So in this case, we actually, given that our level of connectivity or our selection of hub nodes is based on degree, in our null model, we shuffle the network, but we keep the degree sequence. And then we also measure in the null model the level of connectivity between the nodes of a certain level of degree, which in this case gives us the light gray line. And then we take the ratio between the two, expressing how many more times do the hubs in our network of interest have a higher level of connectivity than you would expect in the random null situation. In this case, the degree-preserved random network. Now, preserving the degree is really crucial here, because otherwise we would just end up with the dark black line saying that we would basically overestimate the level of connectivity, because, well, high-degree nodes would, on average, always have a higher level of degree. So here the null model is really crucial if we want to select a rich club type of feature. Now others, so we, in this case, right, we selected the level of richness, as people tend to call it, on the basis of degree, right? So we're counting the number of edges per node, and then we're expressing the subset of nodes as a rich club or a club that has high richness in the overall network based on the number of connections that a certain node has. And there is an equivalent weighted version of this. But people said, why not take other metrics, right? We can have other centrality metrics, as we discussed. And one of these suggestions was actually recently made, saying, well, why not take the participation coefficient, right? So why not select those nodes as hubs that actually share a high level of participation coefficient, meaning that there are like really truly connector hubs in the network, and then look at the level of connectivity between them. And this was proposed as the diverse club. And others have also said, why not do this on not on participation coefficient, but for example, other types of metrics of integration. And this was, for example, also proposed as the club of binding nodes, or the binding club. So once we have established our hubs, then, and we looked at the rich club structure or the core structure in nervous systems, how can we compare them, or how can we use this metric or this property of the network when we want to do a case control study? So the simple answer would actually be, well, just use any type of statistics that you're so familiar with. So if we would do this, if we would just compute the level of connectivity or centrality for every one of the nodes in the network, we can then just do a simple control patient test by using a t-test or a permutation test. We can basically use any type of statistics like an ANOVA or a t-test or any type of other simple statistical test to assess the level of connectivity per node in the network. But there are also, people have also suggested more advanced type of comparison. In particular, when they looked at the overall distribution, right? We can, in option 1, we would simply test the level of connectivity per node in the network. So we would do a node-based type of analysis. But what if you would be interested in seeing whether the entire distribution of connectivity would be different? So one of the options was proposed by Temenon and colleagues, in which they said, well, we can also look at the degree distribution. So in this case, they said, what if we would take the degree distribution over the entire average population, and then for every one of the individuals, we compute how well the individual distribution correlates to the global average type of degree distribution. And we do that for our patients in controls. So for every one of the individuals, we get a correlation coefficient actually expressing how well the individual degree distribution fits to the normal population. And then if the patients would be different, then their correlation coefficient would be, so the distribution would be different from the average distribution, so therefore the correlation would be low, and that's actually what we can test between the two populations. So this might be a way to test the entire degree distribution. So in the final minutes, I want to talk a little bit about basically general things to think about when you're analyzing hubs. So, and these are, like I said all in the beginning, these are open questions. I think so far there's a little bit of consensus in the field on how to select hubs and perhaps on core structure or rich club structure in nervous systems. But the big open questions now is on how to compare these hubs, and in particular also how to, what type of things we should consider when we select those hubs, and what might actually influence our definition of hubs in when we analyze networks. And one of the first things that I think is worth to notice is this was nicely formulated by Power and colleagues a couple of years ago, is that the community size, or basically the size of the submodule a certain node in, might actually influence its functional degree. And this basically, the idea is the following. So let's assume that we have this type of toy network, and we just look at the two different types of functional connections. So if we look at the long-range connection, so this will be a level of functional connectivity or correlation, right, as we measure it, between nodes that are relatively spatially apart. On average, their connectivity will be a little bit lower, as compared to nodes that are more closely together, both in spatial as well as in more topological space, right, which will be the short-range connection. Now the thing is that if a node, right, is participating, like these two nodes, if a node is participating in a relatively large module, that means that apparently it has a lot of topological neighbors. The module is large, so there are many more nodes in a certain module than there are in the others. Now, given the nature of functional connectivity, it is very likely that the node that participates in a bigger module, because it has more functionally connected neighbors, that it will also have a higher number of functional edges that will survive the thresholding procedure that we will use. So basically what will happen is that the larger module will have a little bit higher bias to finding more centrally connected hubs in that module. So the bigger the module, right, the higher the probability that the nodes in that module actually have a higher level of functional degree, because, well, that's the nature of the modular decomposition. And this might in particularly, as shown by Power and colleagues, for example, hold for the default network, which is around 25% of the brain. So therefore, every one of the nodes within the default mode network would have actually a certain level of bias to indeed include a high level of high connectivity node, with the far majority of those edges very likely to be connected to the other nodes of the default mode network. So this might be something to consider when you use functional connectivity to select your connected hub nodes in the network, that you might have a little bit of a bias, or at least there's an influence of modular structure to the selection of hub nodes. And this was also nicely illustrated in this complex slide. You can forget about the details, but the point here is that there's like I said, a bias towards finding more functionally connected hub nodes in larger modules. Now, the second topic I want to discuss is the influence of false positive and false negatives on degree. Andrew already pitched this work in which people in the last years started to notice that actually the false positive and false negatives might have a different influence on network structure. And Andrew was actually was the first to show this very nicely, that false positives can have a stronger influence than false negatives in network reconstruction. And together we then followed this up and said this can have quite severe influence on case control studies. And Andrew already mentioned this, that the inclusion of a little bit more false positive, in particular when you do proportional thresholding, can lead to a more random type of organization in your group, most often the patient population. And in consequence, this can have an influence on when you measure the smallworldness or clustering or path length metric. So how does this effect relate to the selection of hubs, right? Are hubs secure from this effect, or are they potentially also influenced? So Andrew's paper, and together with our case control paper, basically followed this type of argument. So low functional connectivity, if you would have a network that is based on having on average a low functional connectivity, then you're a little bit more likely to include a few false positives when you do proportional thresholding. Now, false positives have a stronger effect on network topology than false negatives in terms of giving a different clustering coefficient or different path length. So as a conclusion, we could argue that if we would have a network based on lower functional connectivity, then the overall network would be a little bit more random, showing a shorter path length and a lower clustering coefficient. Well, this is found by the other papers. Now, going all the way back to the beginning, to the Barabasi paper, we already learned that random networks can actually have a different type of degree distribution, right? Because they had this bell-shaped curve, while the ones that are a little bit more structured or actually displaying hubs, they might tend to show a little bit more of this right tilt or heavy tilt, or in the extreme case, a skew-free type of power law distribution. So the more random the network is, the more different the degree distribution will be, or it will look a little bit more to the bell-shaped curve function. So if we would have two populations with the patients showing a little bit lower, on average, a lower functional connectivity, we can conclude that their network will be very likely to be a little bit more random. So as a result, they will automatically have a little bit of a different degree distribution. So just by lowering, or just by having a network with a little bit lower, based on lower functional connectivity, we can, by this line of reasoning, argue that there might be a little bit of a bias of finding individual differences in hub distribution, which might be more related actually to the lower functional connectivity. So if you would have lower functional connectivity in one of our groups, most of the time the patients, then this might lead to a more randomly distributed hubs in the network. The hubs might be, or the total level of degree might be more distributed across the nodes in the network, given the random organization of the network. So as a result, if we just select the top 10% highest degree nodes as essentially connected hubs, then automatically the hubs will be a little bit more randomly distributed. And so when we take these more advanced options, we have to take this into account, right? If we would just, for example, compute our relationship of the average distribution of the entire group with our individual degree distribution, then if one of the groups actually has a different level of overall functional connectivity, as a result, we might automatically find different relationships. So here too, basically the underlying lesson is when you go into the more advanced options, then also the problems will get automatically a little bit bigger, or the things that you have to think about. So, and finally, one word about the null condition. We already had, of course, before the break, we saw the high importance of the null distribution and the influence of that on when we select our metrics. And I already mentioned in this case, when we select a rich club, that when we base it on degree, then we have to have a good null distribution to be able to select a rich club property. So, and the importance here is that, well, the degree, when the degree increases, the level of connectivity between those hub nodes will always go up, right? Now, in the case of when we're selecting our centrality on the level of degree of a node, this is relatively easy to fix, because in the random condition, we can keep the degree of the nodes equal. And that is simple to do. But if we select our nodes, or hub nodes, on basis of other centrality metrics, for example, the participation coefficient, or the between centrality, or some of the other metrics, this might not be as trivial. Because as far as I know, there are not really good null conditions to keep the between centrality of a node fixed, or the participation coefficient of a node fixed, over a subsequent level of increasing level of those metrics over the nodes. And as a result, if our null condition is not really properly tuned to the metric that we're examining, then perhaps we might have an overestimation or underestimation of our richness of the central nodes of the network. And then as a result, this might in turn have an effect on our case control study. So this is really something to keep in mind when you go into the more advanced and you want to take other metrics of centrality, then really think properly about your null model. And like I said, this is not an easy job to do, and I think there are many open questions to this in the field. So in summary, we've talked about hubs, we've talked about strategies to measure these hubs, to label these hubs, and we saw that there are different flavors of hubs, and we talked about different strategies to measure properties of richness between hubs and their overall core structure in the network. And finally, we talked about a little bit more advanced options, in particular some biases or potential things to think about when you select your hubs in terms of structural and functional connectivity. Thank you for your attention.